Let us now discuss another application of multiple integrals, that is in determination of moment of inertia. Moment of inertia of a plane lamina as well as that of a solid can be determined with the help of multiple integrals. But before we go for the definitions of moment of inertia in terms of double and triple integrals, let us initially recollect what is the classical definition for moment of inertia. Suppose a particle of mass m is there, then what is its moment of inertia about a line? Its moment of inertia is defined as mr square if r is its distance from the line. On the other hand, if you have got a collection of particles of masses m1, m2, m3, etc. with distances from the fixed line as r1, r2, r3, etc., the moment of inertia for the collection of particles can be defined as sigma mi ri square. And there's one more point. Suppose the moment of inertia of a body of mass m can be expressed in the form mk square, then k is called the radius of gyration. We also make use of two theorems, parallel axis theorem and perpendicular axis theorem. Suppose we want the moment of inertia of a body about a line L dash. If it is denoted by I dash, then I dash can be written in terms of the moment of inertia about a line passing through its center of gravity and parallel to L dash, and then another quantity. In fact, I dash can be written as I plus ma square. What is I dash here? I dash is the moment of inertia of the body about the line L dash. What is I? I is the moment of inertia of the body about a line passing through the center of gravity and parallel to L dash. What is m? M is the mass of the body. What is a? A is the distance between the parallel lines. Let us then recollect what is the perpendicular axis theorem. Suppose the moment of inertia about two perpendicular lines is known. Let us denote them by I1, I2. Then the moment of inertia about a line perpendicular to the plane and passing through the point of intersection of the earlier two lines. That is, if you denote it by I, then you can write it as I is equal to I1 plus I2. To understand this, let us consider a particular case. Suppose the moment of inertia of a plane lamina of the xy plane about the x-axis and y-axis, that is Ix and Iy, are known. Then the moment of inertia of the lamina about the z-axis, that means the line passing through the point of intersection of the x-axis and y-axis, denoted by Iz, is given by Iz is equal to Ix plus Iy. Then let us consider a plane lamina occupying a region R of the xy plane. Let mu be the mass per unit area. Then the moment of inertia of the lamina about the x-axis, denoted by Ix, is equal to double integral over the region R mu y square dx dy. Similarly, we can define the moment of inertia of the lamina about the y-axis as Iy is equal to double integral mu x square dx dy. Then let us define the moment of inertia of a solid. Let us consider a solid occupying a region V of space. Let ρ be the density or the mass per unit volume. Then the moment of inertia about the x-axis is Ix is equal to triple integral over V rho times y square plus z square dx dy dz. Here y square plus z square is the square of the distance of any point xyz from x-axis. Now we go for Iy, or the moment of inertia of the body about the y-axis. That is defined by the integral triple integral over V rho into z square plus x square dx dy dz. Here z square plus x square is the square of the distance of any point xyz from the y-axis. Now the moment of inertia of the body about the z-axis, that is defined by Iz is equal to triple integral over V rho into x square plus y square dx dy dz. Let us discuss one problem on determination of moment of inertia of a plane lamina and another problem on finding moment of inertia of a solid. The first problem is find the moment of inertia of a circular plate about a tangent. What is the procedure we are going to adopt? We assume that the plate is confined to the xy plane. Initially find out the moment of inertia about the z-axis. Using perpendicular axis theorem, it can be written as sum of the moments of inertia about x-axis and y-axis. By symmetry, we can determine what is the moment of inertia, say for example about y-axis. Then about the required line, that is the tangent line, can be determined. Initially, let us mention that the plate is confined to the xy plane. Let the plate be confined to the xy plane with its center at origin and radius is equal to a unit. Let rho be the density and m be its mass. Then m can be written as rho times pi a square. Let us now consider the moment of inertia about an axis passing through its center and perpendicular to its plane. That means we are taking moment of inertia about z-axis. Iz is equal to double integral over the region R rho times x square plus y square dx dy. Because given is a circular plate, let us introduce polar coordinates. We replace x square plus y square by r square dx dy by r dr d theta, and the limits for r 0 and a, limits for theta 0 and 2 pi. From the earlier relation, m is equal to rho into pi a square, rho is m by pi a square. So we get Iz is equal to m by pi a square into integral theta is equal to 0 to 2 pi, integral r is equal to 0 to a, r square into r dr d theta. What is the reason for this? Because we want to express the moment of inertia in terms of the total mass. That is why we have rewritten in this fashion. Performing integration with respect to r, we get m by pi a square into r to the power 4 by 4 to be evaluated at the limits 0 and a, multiplied by integral theta is equal to 0 to 2 pi d theta. Substituting the limits and integrating with respect to theta, integral d theta is theta, substituting the limits you get 2 pi. Therefore, finally we get m a square by 2. From perpendicular axis theorem, we know that Iz is equal to Ix plus Iy, or because of the symmetry of the plate about the coordinate axis, you can as well write it as 2 times Iy, or Iy is equal to ma square by 4. Now, from the figure, moment of inertia about LL dash or the required line or the tangent line is equal to moment of inertia about the y-axis plus capital M into a square. Because a is the radius, a becomes the distance between the two parallel lines. Here, because of this symmetry, O becomes center of gravity. OY will be the line passing through the center of gravity. LL dash and OY are parallel to one another. Therefore, moment of inertia about LL dash or the required tangent is equal to MA square by 4 plus MA square or 5 by 4 MA square.